Every system is made of parts, and those parts have to talk to each other. But how closely those parts are tied together turns out to be one of the most consequential decisions in software architecture. In this video, we explore coupling, what it is, why too much of it is dangerous, and how to deliberately reduce it. Imagine you need to change how your system calculates a price. Simple enough, except that logic is copied into the checkout service, the reporting service, and the mobile API. Now every team is involved, every deployment is coordinated, and a mistake in one place cascades into three others. This is the pain of tight coupling. Your components know too much about each other, so changing one forces you to change them all. Think about the difference between a lamp that is hardwired directly into your wall and one that uses a standard plug. The hardwired lamp is tightly coupled to the building. You cannot swap it without rewiring. The plug-and socket design hides all that complexity behind a stable, agreed-upon interface. Either side can change as long as the socket stays the same. That is exactly what loose coupling achieves in software. The top row shows loose coupling. The order service publishes to a stable interface, an agreed contract or a message bus, and the checkout service receives from it. Neither side needs to know the other's internals. The bottom row shows tight coupling. Order service calls checkout, reporting, and the mobile API directly. Every consumer is wired to the producer. Add a new consumer, or change orders internals, and you must touch every one of those connections. When the order service finishes, it does not call anyone directly. It publishes a single event, something like order placed, to a message bus. The bus is the only thing order knows about. Downstream services, checkout, reporting, notifications, subscribe to that event, and each handles it on their own schedule. Adding a new subscriber requires zero changes to order service. That is the key consequence. Producers and consumers evolve independently. Tight coupling has one genuine advantage. The call chain is right there in the code, easy to follow in a debugger. But you pay for that convenience every time the system grows or changes. Loose coupling inverts that trade-off. You gain independent deployability and easy testing, but you introduce indirection. You can no longer just read the code top to bottom to understand what happens next. You have to follow events or interfaces. Neither is free, but for systems that must evolve, loose coupling is nearly always the better deal. You reduce coupling with three main tools. First, define stable interfaces. Both sides agree on a contract, and the implementation behind it can change freely. Second, apply dependency inversion. A high-level component should depend on an abstraction, not a concrete lower-level one. Third, use asynchronous messaging to decouple not just knowledge but timing. Producers do not wait for consumers. A practical test. When you change a component, count how many other components also need changing. If the answer is often more than one, your coupling is too tight. Coupling is about the blast radius of change. Tightly coupled systems mean a change in one place echoes through many others. Fragile, slow to evolve, and painful to test. Loose coupling draws a clear boundary. Components agree on a contract, hide their internals, and communicate through stable interfaces or events. The result is a system where each part can grow and change without dragging its neighbors along.